Okay, so we're going to be continuing our new topic of crude oil and fuels, looking more at what alkanes are and also combustion reactions of alkanes. So just to start off with recapping the definitions that you should have looked at last week. So the first one is boiling point, and this is the temperature at which liquid boils. Our volatility is the tendency to turn to a gas. Our viscosity, how easily it flows. Now this one often causes some confusion. So high viscosity means that it's difficult for it to flow. So I always like to use honey as an example of something that is very viscous, whereas water is not very viscous. So water flows very easily, whereas honey, it's quite gloopy, it doesn't flow as easily. Flammability, this is how easily it burns. So in last week's work, we were looking at fractional distillation, and that was using the property of boiling point in order to separate out hydrocarbons, so molecules containing just hydrogen and carbon atoms. They were using the boiling point in order to separate those out. So at the top, we got the shorter chains as they have much lower boiling points, whereas at the bottom you have your long chain hydrocarbons which have a much higher boiling point. Now the other properties, volatility, viscosity and flammability, as well as colour, also tends to follow a pattern linking to the carbon chain length. So our volatile substances are ones that are able to turn to a gas easier. They are also our shorter chain molecules. So our methane is very volatile. Our viscosity, if you think about the uses of some of these, so right at the bottom of that fractionating column, you get the residue, which contains hydrocarbons that are used for things such as tarmac, so to make our roads. And so if you think about how easily that flows compared to, say, petrol going into a car. Petrol is a shorter chain hydrocarbon than the hydrocarbons used for tarmac, but it is a much lower viscosity as it flows much easier. Tarmac, a bit more like honey, where it's gloopier, harder to flow. So our longer chain molecules have a higher viscosity. And then finally, flammability, how easily it burns. Again, our shorter hydrocarbons, they are much more flammable. So our gases such as methane, which we use in our Bunsen burners, we can see that they are flammable as we use it to light our Bunsen burners. The other thing to consider is colour. So I've said that tarmac is a long hydrocarbon chain, and we can see that colour being very dark, quite black. If you compare that to a shorter hydrocarbon chain, something that you might have in your house, such as vegetable oil, that's much more of a yellowy colour. So our longer chains, they're also darker in colour, and our smaller chains are lighter in colour. So we've just recapped those properties. So small hydrocarbons, their boiling point is low. Large, it is high. Volatile, our small hydrocarbons have a high volatility, very easy to turn into a gas. Our large have a low volatility, very difficult for them to turn into a gas. Viscosity, our small hydrocarbons have a low viscosity, it's easy for it to flow, whereas our large hydrocarbons, they have a high viscosity, it's much more difficult for it to flow. Flammability, our small hydrocarbons, they are much more flammable, whereas our large hydrocarbons, they have a much lower flammability. Something you might have also looked at earlier on in your science careers is the fire triangle. And so these are the three things which fire needs to continue, or to start even. So it needs a fuel, it needs heat, and it needs oxygen. So a fuel can be something like the methane that we use in our Bunsen burner. Oxygen is in the air around us, and heat is going to vary as to how much heat you need, but of course once a fire starts, heat is quite plentiful supply. However, taking away the fuel or taking away the oxygen would stop that fire from happening. So our smaller hydrocarbons in our crude oil, they're the ones with the higher flammability, and they're the ones that we use as fuels. So combustion, you will have looked at this definition before, but what it means is you're burning that substance in oxygen. So for example, burning methane in oxygen. However, what we're going to look at is that there are actually two types of combustion. Complete combustion, where you have plenty of oxygen around your reaction, or incomplete combustion, where there isn't quite enough oxygen for it to completely combust. And we're going to look at how that makes a difference to the products that we get. So we're still burning in oxygen, but we get different products from these two. Hydrocarbons become oxidized. So we've previously looked that oxidation of substances means that they gain oxygen. So the hydrocarbon is gaining oxygen. I've just said, but the products of combustion are going to differ depending on whether we have complete or incomplete combustion. But in both cases, we're still oxidizing our hydrocarbons. Okay, so hopefully you've already used the BBC Bite Size link to find out what the definition of an alkane is. That it is a saturated hydrocarbon. So this means that it's a molecule which only contains hydrogen and carbon atoms, and that it only has single carbon-carbon bonds. There are no double bonds in an alkane. You also should have looked at the 4 properties that make up the alkane homologous series. So that's that they have the same general formula, they differ by CH2 in molecular formula for each consecutive alkane, and that there is a gradual variation in their physical properties such as boiling points, which we've looked at when we looked at fractional distillation, and also that they have similar chemical properties, which means that they're going to react in the same way, just like elements of group 1 all react in a similar way. Compounds of the same homologous series are going to react in the same way. So our general formula for an alkane is CnH2n plus 2. So these subscript numbers at the bottom, this is telling us the number of carbon atoms in the molecular formula and the number of hydrogen atoms. So for any alkane, you would say that there are n carbon atoms and that there are 2n plus 2 hydrogen atoms. And so we can use the molecular formula of a substance of a hydrocarbon to be able to tell whether it is an alkane or not. So give 2 examples here. So C4H10 and C4H8. So here we have 4 carbons and 10 hydrogens. So using this general formula above, we would say that N equals 4, and therefore we would say that 2N plus 2, therefore is 2 lots of 4 plus 2, which is 8 plus 2, which is 10. And that's how many hydrogens we've got, and so that works, so it's an alkane. Here, we've still got 4 carbons, so N equals 4, so then 2N plus 2, which we've just done, 2 lots of the 4, plus 2, which is 10. However, we have 8 hydrogens instead of 10, and so it's not an alkane. It's not an alkane. So how we can calculate our numbers of hydrogen atoms or carbon atoms is by using our molecular formula. So for example, a question says, how many hydrogen atoms are there in an alkane that has 5 carbons? How many hydrogens? Well, then we know that n equals 5, so therefore 2n plus 2 is our formula to work out our number of hydrogens. So we would do 2 lots of the 5 plus 2, which is 10 plus 2, so there'd be 12. And then from that we can write our molecular formula. So C5H12. They could also ask it the other way around. So an alkane that has 12 hydrogens how many carbons? So here we know that 2n plus 2 equals 12. So then subtract the 2 from each side and we get 2n equals 10. So then n equals 5, and that's our number of carbons. So we can also write our molecular formula C5H12. So you could ask it either way round. There are certain alkanes that we need to know, and that is methane, which I've already talked about, so that's the one we use in Bunsen burners, ethane, propane, and butane. You'll notice they all end in ane, and that is what tells us that it is an alkane. These are consecutive alkanes, so each one we are adding CH2 each time. So methane, we start off and this just has 1 carbon, so I'm going to do another column number of carbons. So 1, 2, 3, 4. And we can use our general formula of CnH2n plus 2 to work out our formula, or you could learn it. So methane, 1 carbon, then n is 1. We don't write 1, just like in H2O, it's not H2O1, it's just H2O. So n is 1, so then 2 lots of 1 is 2, plus 2 is 4, so then there are 4 hydrogen atoms. Ethane, we know we're adding CH2, but we could also use our general formula. So n is 2, and so then 2 lots of 2 is 4, plus 2 is 6, but you can see we're just adding that CH2 each time. Propane, n is 3, number of hydrogens, 2 lots of 3 is 6, plus 2 is 8. Butane, C4, 2 lots of 4 is 8, plus 2 is 10. So they are our 4 that we have to know. We also need to be able to recognise the structure. So each carbon just has single bonds, either just to hydrogens or to an additional carbon atom. Might run out of space for butane, but hopefully you're getting the idea that we just use a stick to show bond between our atoms. Butane 4, showing our bonds between our carbons, and our hydrogens. This is what's called a displayed formula, as we're showing all the bonds that are in our compound. So these 4 alkanes that we've just looked at, they are quite useful as fuels because they are short chains. Reason for that is that they have a high flammability, which means that they ignite quickly. They're also useful as gases, and so they are also better in that respect. They also will release energy on combustion, so it's an exothermic reaction. And so our difference between complete and incomplete combustion, I've already said, is that it depends on the amount of oxygen available. So in complete, we have plenty of oxygen, whereas incomplete, we have a lack of oxygen. So incomplete combustion, we're reacting an alkane, such as methane, with oxygen. What we're going to make in complete combustion is carbon dioxide and water. So here, 1 carbon, 4 hydrogens, only 2, so we need to double the amount of water we have, so we now have 4 hydrogens. Now check our oxygens, we've got 2, 3, 4, so double our number of oxygen molecules. So here you can see that you're using 2 molecules of oxygen in order to combust 1 molecule of methane. In incomplete combustion, there are 2 possible products. So the first is carbon monoxide, so a carbon with just 1 oxygen attached to it. We still always get water, as that is needed for our hydrogens. So here we've still got 4 hydrogens, so we're still going to need 2 water molecules to make sure that we've got 4 hydrogen atoms on our product side. But our oxygens now, 1 and 1, and our oxygens now 2, 1, 2, 3. So in order for this combustion reaction to happen, we have to have 1.5 oxygen molecules compared to 2 molecules. So there's less oxygen that's being used in this incomplete combustion compared to our complete. If we're looking at just 1 molecule of CH4, in order to remove the fractions, we could just double it all. So 2 CH4 plus 3O2 goes to 2 CO plus 4 H2O. It's the same equation, but here we're using whole numbers instead of having that awkward fraction. However, that fraction shows a clear comparison that here we're using less oxygen than in our complete combustion. So forming carbon monoxide is one of the options, but alternatively, if we have even less oxygen, we might just simply form carbon itself as a soot. Still 2 H2O, so that we have those 4 hydrogen atoms, 1 carbon, 2 oxygen, 2 oxygen. So this one's all nicely balanced. But as you can see, depending on the amount of oxygen that's being supplied, is going to depend on what our products of combustion are. This carbon is a solid soot, whereas carbon monoxide and carbon dioxide are gases. Normally when they talk about incomplete combustion, it is carbon monoxide that they're referring to. Often they'll flag this by saying the gaseous product formed from incomplete combustion, but sometimes they might ask about a solid residue, that's formed as a result of incomplete combustion, and that's your solid carbon, your soot. So our products of combustion: carbon dioxide plus water for complete combustion, whereas for incomplete, our products is carbon monoxide plus water, or carbon soot plus water. So it's important to read the question to know which of those products they're going to be after. How we can detect our products of complete combustion. So carbon dioxide, we test for using lime water. You might have come across this before, but we will definitely be looking at it when we go back. So lime water is calcium hydroxide, and so when we bubble through carbon dioxide gas into lime water, it ends up turning cloudy, and that's because it forms calcium carbonate, and that is a solid precipitate. Calcium carbonate is chalk, so you can think of that white solid, and so our lime water turns cloudy if carbon dioxide is present. To test for the water, there are a few things we could do. First thing is to observe condensation, as you call it in an ice bath. The other thing we could do is we could test for it using cobalt chloride paper, and this will turn pink if water is present. And the third way, which you can at least picture the outcome of this, is using copper sulfate anhydrous crystals. Now, anhydrous means without water. We're used to our hydrous copper sulfate crystals, which means they've had water added to them. And our hydrous copper sulfate crystals is what we made back in autumn term, so those nice blue crystals that we made. If we were to evaporate off all the water, boil it to dryness, we would find that it would form white crystals, and that's the anhydrous version. So if water is present, those white crystals would turn blue. Carbon monoxide. You might have a carbon monoxide detector in your house, particularly by your boiler, as that will detect whether any incomplete combustion is happening in your boiler. That's important because incomplete combustion, you have less energy released, so your boiler wouldn't be as efficient. But even more importantly, carbon monoxide is very dangerous, as carbon monoxide binds to hemoglobin. And for those of you who don't remember, but you might have looked at it in biology, your red blood cells contain hemoglobin, and it's this hemoglobin that carries the oxygen around your body in your blood. And if carbon monoxide binds to the hemoglobin instead, it means that the oxygen can't be transported around the body as well. And so carbon monoxide poisoning means that your oxygen can't get around your body as effectively, which obviously causes problems as cells can't undergo respiration, etc. Importantly though, carbon monoxide is colourless and odourless, and so it's very difficult to detect. So our carbon monoxide detectors will detect it, however you yourself would not be able to detect the carbon monoxide. That's why it's important to have carbon monoxide detectors so that you're not at risk of carbon monoxide poisoning. How to balance equations of combustion. I'm giving you an example of methane, showing you how to do the complete combustion and incomplete combustion, and if you're going to end up with a fraction, because here we had 1, 2, 3 oxygen atoms, but they come in pairs, so 3 divided by 2 is 1.5 in order to make that 3 atoms of oxygen. But you will probably prefer to just times it all up by 2 to get rid of the fraction, like I've done here. So 3 times 2 is 6, 2 plus 4 is 6. So have a go at doing the balanced symbol equations for the complete combustion of butane and the incomplete combustion of butane to form carbon monoxide gas. There's also a couple of exam style questions for you to have a go at, for those to be submitted on Teams. However, there is some bond energy calculations, so the stuff we were doing on exothermic and endothermic reactions. So if you watch the DIRT video I've done based on your EduCake and bond energy calculations first, then this will help you with those questions. Thank you for watching.